let us start. Now we discuss the different conditions, velocity profile, entrance condition in case of laminar flow. So you already saw that because in laminar flow we have regular paths for flowing fluid particles, molecules. That's why you saw that simple mathematical analysis we did, and we were able to derive the equation for shear stress as well as the velocity profile in the flow that occurs in the pipe. Now, next we discuss the turbulent flow. So turbulent motions are very common in nature. As you can see that practically all the fluid flows that occur that are commonly turbulent flows. So laminar flow, that is rare in water systems. But still we study laminar flow because, as I said, simple mathematical analysis possible, and we can understand, it helps us to understand the behavior of the turbulent flow, which is complex. So in turbulent flow, we saw that the particles of the fluid, they move haphazardly in irregular paths, or they will move with high velocity, consequently high Reynolds number. So essentially, the velocity, that is a three-dimensional, because there are fluctuations. Since we have turbulence, you can see here in these diagrams. So in this case, if you consider the velocity, that is essentially three-dimensional. In laminar flow, we can assume the velocity to be a one-dimensional, but in case of turbulent flow, essentially it is a three-dimensional flow. And this is how it becomes very complex. So that's why mathematical analysis is very difficult. Clear? Let us proceed. Now, turbulent flow in pipes, as you can see here, that these are the fluid particles or molecules that will move in regular paths. You can see here they move in regular paths. But when we have the turbulent flow, after turbulent flow, you can see here they mix together because of the turbulence. Clear? So in this case, you see in this diagram that the particles of this fluid water here, molecules, they are moving in irregular paths. So this we classify as turbulent flow. Now in turbulent flow, let's say if I consider u is the velocity in x direction. So if I consider that velocity with respect to time, what is happening, you can see that this velocity is changing. These are the fluctuations of the velocity. Clear? Along the x direction. Similarly, it will be in y and z direction. So you can see that if I want to calculate the velocity, the instantaneous velocity at any instant, then this will be equal to the time average velocity. This u bar, this is the time average velocity. If I average all these fluctuations, what I get this straight line, which is shown here. This straight line here, which is shown here red, this is denoted by u bar. This is the time average when we average these fluctuations. So at any distance, if I want to calculate the velocity, it will be equal to that average, time average, plus u dash. This is the fluctuating component. And this fluctuating component can be plus, can be minus. It can be plus, it can be minus. You can see above the line, below the line. So this is how it makes these velocity calculations in turbulent flow complicated. And this is only I consider in x direction the velocity. So what we have is that the intense mixing in turbulent flow, it brings particles at different momentums into close contact and thus enhances the momentum transfer. So what will happen? It says that because you see these layers, they move with different velocity. If you remember previously the laminar flow diagram that you saw, a parabolic, if you draw the layers, they move with different velocities. So what will happen that when these come in contact due to the turbulence, then what will happen? You see this mixing happens, and this mixing happen, it will bring about the momentum transfer. So it means that any particle in a fast moving layer that enters into a slow moving layer, it will try to slow down that layer motion. And if from a slow layer moving, any particle enters into a fast moving, it will try to slow the fast moving layer. And from the fast moving layer to the slow moving layer, it will try to speed up that one. So this is how the momentum transfer occurs. And this is how then we achieve the velocity profiles. Clear? So these fluctuations of velocity that you see here in this diagram, these fluctuations of a velocity component u with time at a specified location in turbulent flow. And these will change as the turbulent conditions continue. These will change. You cannot say that this graph will continue like this. It will change. It will depend on the turbulence of the flow. So the instantaneous velocity fluctuate about an average value. You can see here this horizontal line is the time average. So the instantaneous velocity will fluctuate about this, which suggests that instantaneous velocity u can be expressed as by this equation that I already explained. So the instantaneous velocity at any instant, that will be equal to u dash, the time average, plus the fluctuating component. Clear? So that's why, for example, here the time average velocity, and then you have this u dash here. So at that instant here, it will be u will be equal to u bar plus u dash. Now you can see here that we have this velocity profile, this line, it shows this velocity profile here that you can see. This is the velocity profile that we can draw. Now in this profile, you see that we have a layer which is moving with a velocity u. And then you can see here this velocity is more. So the velocity of this layer fluid particles, they will move with a velocity u plus delta u. So now whenever a fluid particle which is moving here, it enters into this fast moving layer. So what will happen? It will try to slow down this layer. It will bring a velocity change as long as the velocity profile is changing. Remember, we are talking about that. So it will try to slow down this layer. And any particle which is here and it enters into this layer, it will try to speed up. So this is how the momentum transfer occurs. And because of this transferring of the particle from this layer to upper layer, lower layer to upper layer, or upper layer to lower layer, you see that because of this momentum transfer on this plane AB, it will produce a shear stress. On this plane AB, it will produce a shear stress. You can see here top. So because of that, this shear stress will be generated. And now we will look how to calculate this shear stress. Clear? So now before that, in this case, you see this layer is moving with a velocity u, and this layer is moving with a velocity u plus delta u. Clear? So when a molecule enters into this layer, it will try to slow down this layer. Because its velocity is less, it will bring a change that will be negative for this velocity. It will try to slow down here. But if any particle enters from a fast moving layer to a slow moving layer, it will try to speed up there. This is how the momentum transfer occurs. Clear? So in this case, because these particles, you see, if we consider a plane here AB, so because of this momentum transfer, this shear stress will be generated here, this top. And now because of this, you are interested to know that how much is the shear stress generated. Just like we saw in case of laminar flow, what we have in case of laminar flow, that the shear stress that is generated is given by mu into du by dy. This is the shear stress that you can calculate between any two layers. You remember, we can calculate tau naught, and then we can calculate tau at any radius r from the center of the pipe, correct? So we use that equation. And now we are exploring how to calculate this shear stress in case of turbulent flow. So now for laminar flow, you use this equation to calculate the shear stress. But this equation is not applicable in case of turbulent flow. Clear? Because of turbulence. So now before we come to explain how we calculate the shear stress in turbulent flow, we are looking at how the momentum transfer occurs. And because of that, between the layers, this shear stress is generated, and we are interested to calculate this shear stress. Now, if we look to the laminar flow, in case of laminar flow, what happens that molecules, individual molecules, they move from one layer to another layer. You can see from the lower layer, the particle may move to the upper layer, and from the upper layer, the particle can move to the lower layer. And through these individual molecules, the transfer of momentum occurs. But if we consider the turbulent flow, so in case of turbulent flow, what we have? Rather than molecules, we have a finite fluid of mass, what is known as ED, pockets of fluid particles, or otherwise we say in fluid mechanics EDs, pockets of fluids that have a swirling, rotating effect. So what we do is that rather than molecules, as in case of laminar flow, in this case, these pockets of fluids, they basically move from one layer to another layer. For example, from this lower, this ED will move into this layer. And similarly, from this layer, this can move to this layer due to turbulence. And as a result of these EDs, and then these EDs, for example, this ED come to this next layer, it can merge with this ED, and it can grow in size, and so on. So in case of turbulent flow, transfer of finite masses across AB occurs, rather than we have molecules. So this is how the transfer of momentum occurs. And as a result of this, on this AB line in turbulent flow, the shear stress will be generated as shown here. So there will be a shear stress. And now we are interested to calculate this shear stress. We already studied how to calculate the shear stress in laminar flow, because the fluid particles, they have regular paths and simple mathematical analysis possible. The equations were simple. Now let us see that in turbulent flow, how we calculate this shear stress. So now we already studied that for laminar flow, this is the equation, but this equation entirely we cannot use for turbulent flow. We cannot use. So for turbulent flow, what we see is that in turbulent flow, the velocity at any point in the flow fluid fluctuates both in magnitude and in direction, as you saw in the previous slide. And these fluctuations result from multitude of eddies. Means multitude, what is multitude? State of being many small eddies that are created because of fluctuations, because of turbulence, by the viscous shear between adjacent particles. So these eddies grow in size and then disappear as their particles merge into adjacent eddies. So we have a large amount of turbulence. So these eddies can merge into one another and grow in size. Thus, there is continuous mixing of particles. This is the important characteristic of turbulent flow. That one advantage of turbulence is we are able to mix the particles of the fluid. If you want to mix any chemical in, for example, water, so you have to create the turbulence. Just like we mix sugar with water, we have to rotate the water, create the turbulence so that it can properly mix. This is one advantage. But when we do the analysis, it brings a lot of complexity. So this turbulence, there is a continuous mixing of particles, and because of that, there is a transfer of momentum. So now we understand that how transfer of momentum occurs. So for turbulent flow, we discuss first expression that is available to us. Now, just like for the laminar flow, we proceed also for the turbulent shear stress. In the turbulent shear stress, we say that this is equal to eta into du by dy. Du by dy is the same velocity gradient, but in laminar flow we use here dynamic viscosity, but in case of turbulence we use here this eta, and this eta is known as eddy viscosity. And this eddy viscosity is not constant. It is not constant, and it depends on the turbulence of the flow, and which can change from point to point along the flow. You understand? So that's why it's not easy to calculate this turbulent shear stress as compared to the laminar shear stress, because in case of laminar shear stress, we have this mu here. So in case of the shear stress, we have this mu. So this is a fluid property, and you can easily calculate. It's available to us for a given temperature. It's available in the form of tables, end of the book. But in case of turbulent shear stress, this eta, which is the eddy viscosity, this is not a fluid property. It depends on the turbulence of the flow. And if the turbulence is changing, this will change. So that's why this eta you will not find from tables. This eta you will not find from the tables. So this is how it makes it difficult to measure this eta. Clear? Now, in case of turbulent flow, the total shear stress, if you want to calculate the total shear stress, that will be equal to the laminar shear stress plus the turbulent shear stress. It has two components. So that's why this will be equal to sum of these two components. If you look to this diagram, you can see that this is now the shear stress diagram. For symmetry, we draw it like this. Now in this case, you see that near the pipe wall, if you remember, we have a viscous sublayer that we discussed before, and we try to calculate the thickness of the viscous sublayer, and I will discuss in the coming slides. So even if we have turbulent flow, this near the pipe wall, we have a laminar-like condition. It's not true laminar flow. Remember, it's not true laminar flow. It is written in the textbook. You read it. It's not a true laminar flow. But near the pipe wall, a like laminar flow condition is created, even though the flow is turbulent. So that is known as the viscous sublayer, where viscosity is a dominant factor. And this is how we use the laminar flow equation to determine the shear stress component near the pipe wall. Clear? But remember, it's not a true laminar flow. It's written in your textbook. So now coming to this total shear stress. So near the pipe wall here, you can see that because of the viscous forces dominating, in that case the laminar flow component has more value and the turbulent shear stress has less value. But as we move towards the center, you can see the laminar shear stress value is decreasing, whereas the turbulent shear stress value is increasing. But of course, at the center of the pipe, the shear stress is 0. So that is why the total shear stress in case of turbulent flow is the laminar shear stress and plus the turbulent shear stress. But remember, in this case, you will see when we solve a problem, the value of the turbulent shear stress will be much, much larger than the laminar shear stress. So you can express this shear stress equation in this forms, where now in this case this epsilon, this is known as kinematic eddy viscosity. So in this equation, later on we may solve a problem, you will see that the turbulent shear stress, this term is many times larger than the laminar shear stress. But anyhow, because near the pipe wall we have a laminar flow condition, it's not true laminar flow, like laminar flow condition, that's why we are using this equation in order to calculate the total shear stress. So this is the first expression that we can use to determine the shear stress when the flow is turbulent flow. Also, we have a more commonly used second expression. These are both are given in our textbook. That's why we need to understand both of them. So to arrive at the second expression for the shear stress, we will apply the momentum principle. As I explained before, that in fluid mechanics, we are commonly using three fundamental equations. One is the continuity equation, second one is the Bernoulli equation, and the third one is the momentum equation. And this momentum equation we will derive because we will study forces in fluid flow, we will study pumps and turbines. There we will apply the momentum principle to calculate the forces in fluid flow. But here we just use the equation to arrive at the shear stress equation in case of turbulent flow. So now in order to do that, first you need to understand, as I said, that equations in case of turbulent flow are complex. Why? You can see here. Let us look to this diagram here. In this case, what we are having is that, let's say we consider the flow of particles in case of turbulent flow. It has a mean velocity u. Clear? That we take the average. So that average velocity, you can see it has fluctuations. This is due to the turbulence. This is how essentially it becomes a three-dimensional. So this velocity u, it has a fluctuation here denoted by u dash. And it can be plus u dash, can be minus u dash, as we earlier saw in the diagram. And it can have fluctuation in the y direction, plus v dash and minus v dash. And when you see a bar, it means we are averaging that. Clear? Over a long period of time, those fluctuations. So similarly in the z direction, it can have minus w dash and plus w dash. So it means that you have one velocity, but it can have fluctuation in the three directions. So that is why if you want to calculate the velocity at a particular instant, it will be given by this equation. So now you know that this velocity has fluctuations, clear, in the x, y, and z direction. So now let us see that we have this momentum equation, which says that this F is equal to the rate of change of momentum. This later on we will derive how we get this equation. This is the momentum equation. Forget about this tau into dA for the time being. So it says that forces in fluid flow, that is equal to rate of change of momentum, and for fluid flow, this rate of change of momentum is equal to rho q delta v. Rho is the density, clear, q is the discharge, and this is the change in the velocity. Final velocity minus initial velocity, difference of the two velocities. And this F then we can relate to the shear stress, because shear stress will be equal to force by area. So now to calculate this force, and then we can divide this force by dA, we can get an expression for the turbulent flow, the second expression. So how to calculate the force? And this is the shear stress. So we come to this diagram. You can see that in this diagram here, we have a velocity u for this layer, and then we have this layer. Now we consider a plane, because we have to calculate the force that we can relate to the shear stress. So now what is happening? That we have this eddy or pocket of molecules, finite mass of fluid. In case of turbulent flow, it has the velocity fluctuations. And the velocity fluctuation in a two dimension is this u dash. This is the fluctuation in x direction, and this is v dash, the fluctuation in the y direction. So it is because of this y direction fluctuation, this is how the discharge occurs in this plane, across this plane, across this area dA. Across this area dA, due to this fluctuation v dash, this is how it occurs. Clear? Because of this v dash. So that is why if I want to calculate the force, then what will be that? You see in this equation, this rho comes here, same as for above, and then Q, because now we have this fluctuating component V dash. So discharge will be V dash multiplied by this dA. So this is how Q is written as V dash into dA. Because of this component, we have this upward movement. And this is the change in the velocity. Clear? Because the change that comes due to the fluctuation u plus u dash minus u. Clear? Because of this fluctuation, the change occurs. So u plus u dash minus u. This now we consider here for this the situation here. So if you simplify this equation, then this u and u cancels out, and what we get? We get F is equal to rho into u dash v dash times dA. Now we bring in this expression here for the shear stress. And what we will get is that we get this expression. Tau is equal to this equation here, this we bring here. Tau is equal to F divided by dA. So this is F and then divided by dA. So this dA cancels out with this dA. And now what we are doing, that since this u dash and v dash, they are changing at every instant. So that is why we need to average them over a period time sufficiently long to include large number of fluctuations. Then the shear stress will be equal to u dash v dash bar. Clear? I will explain from where this negative sign comes. But now for the time being, what we have is that now this expression for the shear stress, it reduces to rho into u dash v dash with a bar average. So this term, this u dash v dash bar is the temporal average of the product of the two velocities, and in modern fluid mechanics theory, this is known as the Reynolds stress. If you study modern fluid mechanics turbulence theory, this term is known as Reynolds stress, because Reynolds was the first person who gave us this basic concept, and that is why, because it is a stress, you see this is shear stress, so it has the stress units. So that's why this term, this is known as Reynolds stress. Clear? So this Reynolds stress, this product, you can see that theory very well explains how to calculate this shear stress, but then the problem is how to measure the product of these fluctuating components over a long period of time. So physically it is very difficult to measure this product. Clear? So that's why then Ludwig Prandtl, he came with the idea of the mixing length L. Because now, although this expression is good, theoretically we derive this, but practically in order to measure the shear stress, we cannot measure physically this u dash v dash product. Clear? So that is why Ludwig Prandtl come up with the idea of mixing length, because now we need to convert this equation into such equation where we can measure easily the quantities. So Ludwig Pendrell, he gave the concept of mixing length, and this mixing length L, how we can define this? This mixing length L says that whenever a fluid particle is here and it tries to move to this upper layer, so it will bring, because it is moving from a lower velocity layer to a higher velocity layer, so it will bring a change in this layer that will be negative. You understand? That will be negative because it is moving from a slow moving layer to a fast moving layer. So it will bring a change in the velocity for this layer that will be a negative. Similarly, for example, what I'm saying here is you move from this velocity to this here. This layer, you move to this upper layer. So what is the velocity component that we move? You move with this V dash. So V dash, it is plus, clear? We have plus V dash. This is plus V dash because we move in the positive Y direction. But you can see that the change it will bring, if I extend this here, the change that it will bring, this here, the change that it will bring, so that will be what? Minus U dash. The change that it will bring in this layer, because it moves from lower velocity region to higher velocity region, so it will bring a change in the velocity. So that change in the velocity is negative. So it means that this plus V, it is related with minus U dash. Plus V dash is related with minus U dash. And this is how this negative sign comes. This is how this negative sign comes. Let's say, for example, we have a layer here, a particle here in this one. So in this case, what is happening? Let's say if I extend it here, this layer, and I extend it here. Now let's say, assume we have a fluid particle here, and then this fluid particle moves to this layer. So now in this case, what is the situation? This will occur due to minus V dash now, because we move opposite to the plus Y. So this is now minus V dash, clear? But as it comes from a higher velocity region to a lower velocity region, it will bring a change in the velocity. So it will bring a change in the velocity that will be positive. So it will bring a change in the velocity as plus U dash. So in this case, you can see that again, if I take the product of that minus U dash V dash, if it moves from lower layer to the upper layer, again you can see plus V dash minus U dash, clear? So that is why how this negative sign appears. It just shows the sense, clear, that how this product is considered. So this negative signs, considering this product, it will give us the positive shear stress. That is why this negative sign, for example, if you study the Indian books, they do not write down this negative sign. They will just write down rho into U dash V dash bar equal to this total shear stress. But we need to write down this negative sign to make the sense correct, so that this product is correctly represented. It means that this U dash and this V dash, this product that we consider, for both cases, either the fluid moves from lower layer to upper layer or from upper layer to lower layer, it will be less than zero, negative. The correlation is negative. Simple to say, the correlation is negative. And when this is negative, then it will make the shear stress that we calculate, that will be positive. So this is how the negative sign comes, clear? We can go into detail. There can be a correlation between the two which can be positive, clear? It is still possible, but we are not going into that detail, clear? Just for simplifying this, because already the turbulent flow conditions are very complex. There can be a situation where the correlation can be positive, the correlation can be negative, and there can be no correlation, because we consider three-dimensional fluctuations. But anyhow, for simplicity of understanding this expression, so In this case, we consider this correlation. It turns out to be negative to just make this shear stress is greater than 0. So this term basically is known as the Reynolds stress, and this basically practically very difficult to measure, physically very difficult to measure. We need to express this shear stress in equation form that we can measure. So Ludwig Prandtl came and he gave us the concept of this length L. And what is this mixing length L? It says that when a fluid particle enters from this layer to this layer, or from the upper layer to the lower layer, in such a way that the momentum in the x direction remains the same, that distance in which this happens, this is known as the mixing length, and it is denoted by L. Now we saw that this is the shear stress is given by this expression, and the minus sign I already explained in detail in the previous slide. So according to now the mixing length theory, what we have is that if we compare the similar triangles, you can see here, if you compare the similar triangles here, so this is delta y now becomes L, the mixing length L, and this difference between the two is due to that fluctuating component, and because it can be plus minus, so that's why it is written in absolute. You understand that plus minus sign is just to correct the sense. This is to correct the sense, but in here you see it is written in absolute value. It doesn't mean that we can just make it negative and bring the net effect there. This negative sign is just used to correctly represent the sense that they represent, remember. So that's why it is written in absolute. And with an average, the time average, clear, because we have large fluctuations. So the time average we need to consider. So now your delta U is equal to U dash bar. So now if we consider similar triangles, this one triangle and one this, so you can see that du by dy, this will be equal to this U dash bar by L. So from here L is equal to U dash bar absolute divided by du by dy. So now from the figure, since delta U is equal to U dash, so that is why delta U, that is equal to L into du by dy, this here, clear? So delta U, which shown here, that is equal to L into du by dy. Then what we do for V dash, because here we can write down in here that U dash is now equal to L into du by dy. So now what about this V dash here? That is shown here, the V dash. So Prandtl argued that V dash, this can be equal to some constant into U dash. You understand? We are assuming that this delta U is equal to, or U dash bar is equal to L into du by dy. We also assume that this fluctuating component in the y direction has the same value, but with a constant c, clear? Because it is proportional, it means V dash is proportional to U dash. So when you change proportionality into equality, we multiply with a constant. So now it means that this component here can be equal to L square into du by dy, and bringing this c into this L. We just bring this constant into this L. So now you see L into du by dy, and then multiply with L into du by dy, bringing c into L, it becomes L square into du by dy whole square. So now what we did is that we saw that this quantity is difficult to measure. Now we express the shear stress in terms of this quantity here. So now in this quantity, these we can measure, because essentially we are expressing this L mixing length in terms of the pipe radius. For example, how we can do it, that the shear stress, this L is in terms of shear stress. Rho is the density of fluid, easily measured. Du by dy you can measure. Clear? You see, already discussed. Now this L in terms of the shear stress, and the shear stress, remember the equation in terms of the radius of the pipe that we earlier write down. So now we can say that we can measure these quantities. And this is how the Prandtl mixing length theory, it works very well in case of the turbulent flow. So if we proceed, the total shear stress at any point in turbulent flow can be then expressed by this. So it will have that laminar shear stress component and now the turbulent shear stress component that we just calculated. So the total shear stress, you can use this equation to calculate. Clear? Now the next question is how to determine the value of L, the mixing length. So Prandtl assumed that the mixing length L is proportional to the distance from the pipe wall. And this was a very clever thinking. Later on it was verified that this length L, it is proportional to the distance Y from the pipe wall. You remember Y is the distance from the pipe wall toward the center of the pipe. So when you change proportionality into equality, we multiply this with K. And this K is a constant, and experiments have confirmed that it has the value of 0.40. And if you study other books, they say that this is the von Karman constant, universal constant. But anyhow, in the present textbook, it is written that experiments have confirmed K is equal to 0.4. So now at any distance Y from the pipe wall, you can calculate L, and then you can use this equation easily to calculate the shear stress in case of turbulent flow. Then the concept of the viscous sublayer, as we already discussed in case of laminar flow. So when the fluid enters, you see, when the fluid enters, it will develop a laminar boundary layer, because first the flow will be laminar and then it changes to the fully turbulent flow. So then in that case, first we will have the laminar boundary layer, as we already discussed. Clear? And then after that, what will happen? There will be a transition to a turbulent boundary layer. And because of symmetry, it will happen from both sides. You can see here. And then those turbulent boundary layers, they will meet, occupy the full pipe. And as a result, we have a fully turbulent flow. We have what? A fully developed turbulent flow. So now, this fully turbulent flow that occurs, the same concept, and then when we have a fully developed turbulent flow, then we will have a velocity profile for the turbulent flow, like we saw earlier in the laminar flow. So the same concept we apply. This R naught is the radius, R is the distance which is measured from the center of the pipe towards the wall of the pipe, and Y is the distance which is measured from the pipe wall towards the center of the pipe. The same concept we are using here as we used in case of laminar flow. Now we are using for turbulent flow. So now in this case, what is happening that when R is above the critical value, flow will become turbulent. But near the entrance, a laminar boundary layer develops and grows in thickness, because you have uniform flow as already shown in the. And when it enters, then how the fluid resistance occurs to the fluid by the pipe, and first it will be laminar and then it will change to the fully turbulent flow. So it means instantaneously we cannot expect to have a fully developed turbulent flow, as we saw already in case of laminar flow. So at a critical distance xc, we can calculate this critical distance xc at which the boundary layer becomes turbulent. And then the boundary layers meet so that we have full turbulent flow in the pipe. And we can have a fully developed turbulent velocity profile. So the transition to turbulent flow occurs at a value when the Reynolds number is 500,000. Remember, this is for boundary layer situation. Later on, we will study another chapter where we have boundary layer theory for external flows. So remember, this is not that 2000 that we have the critical Reynolds number. For boundary layer, the critical Reynolds number is different. Clear? So this is for boundary layer we are talking about, that how the boundary layer changes from laminar to turbulent. So for that case, if you want to, you are interested to calculate at how much distance the laminar boundary layer will change to turbulent boundary layer, you can make this as xc. Let's say this is xc, and now this is the critical one, and this is 500,000. And u is the velocity, mu is the kinematic, nu. This nu is the kinematic viscosity. You can calculate xc. That for this velocity and this kinematic viscosity, at what distance transition from laminar to turbulent boundary layer will occur. Clear? So this distance, clear, the fully turbulent flow that occurs, we do not have a well-defined single equation. This is what is written in your book. The entrance length L. In simple words, the entrance length L here, you see that the full turbulence that forms here. You can see here, as we can write down the equation for the laminar flow to calculate the entrance length L, where we have the fully developed laminar flow. Now in this case, our book says that for fully development flow, there is no single equation because of the turbulence that is changing for the conditions. So that's why it says that it occurs within 20 to 40 times the pipe diameter. This is given in our textbook. If you study other fluid mechanics book, similar to the equation LE that we saw for laminar flow, you can also find the equation for turbulent flow to calculate that LE, the entrance length LE. But in our textbook, they say there is no single equation. So rather, instead of giving equation, they say that this turbulent flow will be fully developed within 20 to 40 times the pipe diameter. So when a fully developed turbulent flow occurs, still in that fully development flow near the pipe wall, in this case here, there will be a thin layer where viscosity will be dominating. As I already discussed in the previous slide, there it's not a true laminar flow layer, but it is a like laminar flow. It's written in your book. Study it, read it. A like laminar flow layer will continue where viscosity is a dominating factor. And this layer is known as the viscous sublayer. Clear? Because viscous stresses are dominating in this layer. So this is about the viscous sublayer that is developed in the turbulent flow. And then we already discussed that this is the equation to calculate the thickness of the viscous sublayer. There is a derivation for that, but I am not going into derivation because of the complexity and to focus more on important ideas. So this is the equation that we already discussed, and we used them before while solving the problem. We can calculate the thickness of the viscous sublayer. And why we are interested to calculate the thickness of viscous sublayer? Because if you remember, we can classify the pipes as smooth pipe or rough pipe or in transitional mode. And this is how you have the friction factors accordingly for that. And based on this, if you remember, we earlier studied that if this thickness of the viscous sublayer, if it is more than E, where E is the absolute roughness, this is the size of the projections that are present on the pipe wall that represents the roughness. If this viscous sublayer thickness is more than E, the absolute roughness, so what will happen? The viscous sublayer completely buries the surface roughness, and the roughness has no effect on friction, and the pipe behaves as hydraulically smooth pipe. We already discussed this idea before, and remember, when we classify the pipe as hydraulically smooth pipe or rough pipe or in transitional mode, these are only just these technical terms that we classify the pipes. This is just for the sake of these technical terms. In fluid mechanics and hydraulics, we just classify the pipes to behave as hydraulically smooth pipe or rough pipe. Clear? And if this E is greater than you see here, if E is greater than 14 times the delta V, or delta V is less than E by 14, we classify this pipe as a rough pipe. Because you can see here, these projections are going above this viscous sublayer, and they will have frictional effect along with the turbulence on the flow, and the pipe will behave as if it is a fully rough pipe. And if we have in between the two conditions, then we say that the pipe behave in transitional mode. So just for the sake of hydraulics and fluid mechanics, based on these conditions, we classify the pipe as to behave hydraulically smooth pipe, or fully rough pipe, or in transitional mode. And you remember these concepts, then we use to calculate the friction factor and to accurately calculate the head losses in pipe flows. And this is how we make our calculations accurate. Now we come to the velocity profile in case of turbulent flow. So you see here that we already studied that in case of laminar flow, the velocity profile that is parabolic. The velocity profile that is parabolic. And we derive equation for that to prove that it is parabolic. Clear? Similarly, the velocity profile for turbulent flow is given by this equation. This is the velocity at any distance from the center of the pipe, at any distance r. From the center of the pipe, you can calculate the velocity in case of turbulent flow. Again, this equation can be derived, but no need to go for derivation to save the time because the equations are complex. Just we need to use this equation and solve the problem is sufficient at this stage. So now in this equation here, you can see that log is involved. And that is why we say that turbulent flow can produce a logarithmic velocity profile, our logarithmic velocity distribution. So it means that this profile here, which represents the turbulent flow, this is represented by this equation here, and it follows a logarithmic velocity profile. In case of laminar flow, it follows a parabolic velocity profile. In case of turbulent flow, it follows a logarithmic velocity profile. And this figure, which is given in the textbook, these velocity profiles for the turbulent flow, smooth pipe or rough pipe here, which are shown here, these are plotted or can be plotted using this equation. Clear? So this is the equation that you can use to calculate the velocity at any distance r from the center of the pipe in turbulent flow. Now we say that it is a logarithmic velocity profile which is more fuller. You can see it is more fuller as compared to the laminar parabolic velocity profile. So let us see that we in this video how to see these velocity profiles. So you see this is for oil and Reynolds number is 1. So we expect a laminar flow. So you can see a parabolic velocity profile as we already derived. So theory and experiment agrees with each other. Now for water and Reynolds number is 10,000. So we have turbulent flow condition. So now a dye is injected in order to visualize the velocity of the moving particles. So you can see here that for turbulent flow, the profile is more fuller. Clear? So this is how you can see that this agrees. You see this equation, which represents the logarithmic velocity profile, agrees very well with the experiment. Clear? Now you can see the turbulent velocity. See the logarithmic profile, it is very well explained by this experiment. Now you see a 3D view and you can see the fluctuations of the velocity in 3 dimensions. See the complexity. Okay. So now the comparison of the two velocity profiles, you can see here that in case of laminar flow, we can essentially treat the velocity as moving in one dimension. But in case of turbulent flow, you see that there are fluctuation because of the turbulence in all the 3 directions. So essentially the velocity profile is shown like this. Clear? You can see here. It is shown. This is how the velocity will occur. And we can model it to be represented by this logarithmic velocity profile. Similar to the logarithmic velocity profile, Blasius, as if you remember, he gave a formula for the friction factor when the Reynolds number is between the limits and we have smooth pipe. When we have smooth pipe and the Reynolds number is between these limits, he give the formula for friction factor. Similarly, he give this formula for the velocity distribution in case of turbulent flow. But this velocity profile, it will be for smooth pipe and the Reynolds number has to be between these ranges. And this equation is known as the 7th root law. So you can use this equation to plot the velocity profile in case of turbulent flow. But this equation has some problems. What is that? Number one, it is not absolutely accurate as compared to the logarithmic velocity profile, and you saw experimentally also, if you use this formula, it's not absolutely accurate, but it is easy to work with mathematically. And if the Reynolds number is above 10 power 5, which is the upper limit, so then an exponent somewhat smaller than 1.7 will give good results. Then an exponent we have to use less than 1.7 in order to get accurate results. So this is another way of representing the velocity profile for turbulent flow, but you can see that the logarithmic velocity profile, and also you saw the experiment in the video, that agrees very well with the practical situation. Now we solve a problem. Now we have test on 70 degree Fahrenheit water flowing through a 9-inch diameter pipe. It shows that velocity is 13 foot per second. Now F value is given to us if at a distance of 3 inch from the center of pipe. Now R is now 3 inch. Remember, R is the distance from the center of the pipe towards the wall of the pipe, and Y is the distance from the pipe wall towards the center of the pipe. So remember, when you solve the problems and R and Y is written, so you should understand how to calculate these distances. Now the total shear stress is given to us, that it is 0.388 psf, pounds per square feet, and the velocity gradient du by dy is given, that it is 6.97 per second, velocity gradient. Clear? So what we have to calculate, we have to find the viscous shear stress, and then we have to calculate the turbulent shear stress, and then we have to calculate in the third part the mixing length L. So now what we do, we have to calculate the viscous shear stress. We need to calculate the value of mu. Clear? So this is not given, but the temperature is given to us. So again we go to table A1 in the appendix of the book, and for this temperature 70 degree Fahrenheit, you will read these values. These are the fluid properties. And now first, we already know that at R equal to 3 inch from the center of the pipe, the total shear stress will be equal to the viscous shear stress plus the turbulent shear stress. So this is given, the total is given. Clear? This is equal to 0.388. Now first we have to calculate this. This is what is part first of the question, that you calculate the viscous shear stress. So now in this case it is easy, because mu comes from here, this mu value you put here, and du by dy is given, this is given 6.97. So you calculate the viscous shear stress. You can see here, as I already stated, very small value. So although this equation we used to calculate the total shear stress for turbulent flow, but it was written that the viscous shear stress has smaller, much smaller value as compared to the turbulent shear stress. So you can see here 0.000 something. But anyhow, for accurate determination, we have to consider this. Now we know the total shear stress, we know the viscous shear stress. So the next part we can easily solve. This is given to us, the total shear stress, and the viscous shear stress we just calculated. Now we can easily calculate this quantity, which is the turbulent shear stress. It is asked you calculate the turbulent shear stress. So now you can easily calculate the turbulent shear stress. So now you can see, compare these two. In the total shear stress, see the effect of the viscous shear stress and the effect of the turbulent shear stress. And in part C, we have to calculate the mixing length L. So in the mixing length L, we need to calculate this L here. So now the total shear stress is given. The fluid property we take from the table. Du by dy is given. So we can easily calculate this mixing length L. And this mixing length L turns out to be 0.771 inches. Let us solve another problem. Now we have oil with specific gravity 0.85 is given. This is the last problem. This is the last problem. So oil with specific gravity 0.85 is given, and the viscosity is given to us. The flow rate is given 80 liters per second, and this is the diameter of the pipe. The absolute roughness is given 0.9 millimeter. First, we have to calculate the total head loss. What is the total head loss? Then we have to calculate the shear stress at the pipe wall, tau naught. Shear stress at the pipe wall, tau naught. And then we have to calculate the velocity at 25 millimeter from the center line of the pipe. So what is the velocity at 25 millimeter from the pipe? R is now 25 millimeter. So remember, if you want to calculate the velocity at 25 millimeter from the center of the pipe, which equation you have to use? Because we have a parabolic equation for laminar flow and a logarithmic equation for turbulent flow. So that's why first we have to determine that for these given condition, what type of flow regime occurs. Clear? And then under these conditions, we have to see that is the pipe behaving a fully rough pipe in transitional mode or a smooth pipe, hydraulically smooth pipe. So first what we have to do, the discharge is given 80 liters per second. Just remember, when you solve the problem, keep the units consistent to avoid any mistake. So now we can calculate the velocity. So the velocity is 4.53 meter per second. Now the specific gravity of oil is given. In order to calculate the density of oil, we can multiply this with the density of water, which we know that density of water is 1000 kilogram per cubic meter. So you can calculate the density of oil. This is the density of oil. Now we calculate the Reynolds number, because I said we have to calculate the velocity and also the friction factor in order to calculate the head loss. So we do not have same formula for laminar and turbulent flow. So first we have to determine that for the given condition, we have laminar flow or turbulent flow. So now we calculate the Reynolds number. This is more than 2000. So that's why the flow is now turbulent. So now you will use the turbulent flow conditions, the equations, in order to solve this problem. So now E by D, the absolute roughness is given 0.9 millimeter. So E by D, the relative roughness, that is 0.006. So now you have the Reynolds number and you have E by D. So from these two, E by D and R value, you will calculate the F. So the F you can calculate from Colebrook equation or from Holland equation or from Moody's diagram. So you will get the value of F is equal to this. Now we use the Darcy-Weisbach formula. So in the Darcy-Weisbach formula, what we have is that length of the pipe is not given. So that's why the length we bring here to the left side of this equation. So we calculate HF by L, means the head loss per unit length now. So the rest everything is known, and we calculate the head loss per unit length to be 0.229 meter per meter. If length is, the pipe is given, that you can multiply, it will give you the total head loss for that entire length of the pipe. Next we calculate the shear stress at the pipe wall. So we already derived this equation that tau naught is equal to F rho V square by 8. So this is, you can calculate the shear stress at the pipe wall. Everything is known, you just plug in the values, and this is the shear stress at the pipe wall, tau naught. And next we use the logarithmic velocity equation. Here you can see the logarithmic velocity equation, because we have turbulent flow. We already determined that we have turbulent flow. So the velocity at 25 millimeter from the center of the pipe. Clear? The velocity at 25 millimeter from the center of the pipe, we apply these equation, everything is known. So the velocity is 5.32 meter per second. This is the velocity of flow at 25 millimeter from the center of the pipe. And finally we calculate the delta V, thickness of the viscous sublayer. We already discussed this equation. You put the values. So the thickness of the viscous sublayer comes out to be 0.1134 millimeter. Now we compare this. So you can see that this delta V is between the two limits of rough pipe and smooth pipe. So that is why we say that pipe behaves as transitionally rough pipe. It means that it behaves in transitional mode. So this concludes the lecture.
Excuse me, sir.
This concludes the lecture.